All right, so our next topic here, continuing on with exponential equations, is we're going to look at something called doubling times. Now, doubling time is the required amount of time for a quantity, and a quantity is just anything you can count, to double. And again, because you're talking about growing, it is a particular type of exponential growth. Applications, unfortunately, some that we're getting really familiar with is the growth of a bacterial culture, or in this case, the growth of a virus. So one of the things they look at is how fast are the numbers doubling. It's an easy way to describe it. Population growth, something we're going to look at in our next unit, financial growth. All are applications of doubling times. How fast a city is growing, how fast your money's growing, how fast a bacteria or virus is spreading. Again, all applications of doubling times. Now we're going to have a couple of formulas, hence the S there, that we're going to use. And the first thing is to find the doubling time, again, which is how long it takes for something to double. So our doubling time, which I'm going to use a big capital D for, is equal to the time elapsed, so how much time has gone by, divided by, line here, the number of times the quantity, again, a quantity is just something you can count, doubled. So how much time went by and how many times did that thing double? That's your first formula. Our second formula is calculating using doubling times. And so we're going to have a formula that's going to be n is equal to n naught, which is n little zero down there, times 2 in brackets, because we're dealing with doubling times. So we adding an extra 100%. So 100% plus 100% is 200%, divided by 100% gives you 2. And then our exponent here is going to be t divided by d. That's a d there in the denominator. Now, what do these things stand for? N is your final amount, whatever you're counting. And not, I guess I'll go n little zero there. No, and you can see the position in the equation. Well, that is your starting amount. It's like your A value. T is the time elapsed, or elapsed time, I should say. How much time's gone by? And D, of course, we already looked at, is your doubling time. All right, so there is our two formulas that we are going to use. All right, so now we're going to look at actually using them. So here we go. Example number 1. A biologist grows bacteria in a petri dish. If on a given day there are 800 bacteria, and 8 days later there is 3,200 bacteria, find the doubling time. All right, so I got my formula where I have D is equal to the time elapsed divided by the number of times bacteria doubled, because that's what we're counting right now. Oops. See if I can stretch this out. There we go. All right. Now, the time elapsed is right here. It's 8 days. Nothing to it. But how many times did it double? That's what I need to figure out. So I'm going to go over here, over on the left here in blue, and I have started off with 800 bacteria. Now, if I double that number, times it by 2, if you will, I end up with 1,600. Then if I take 1,600 and multiply it by 2, my calculator out here, I end up with 3,200. So it doubled once, twice. So it doubled 2 times in that 8 days. And so if I take my 8 days and divide it by 2, I end up with 4 days is my doubling time. All right, now it says find the amount of bacteria after 16 days. Now, there's a couple of ways to do this. Number one, and here's why actually, because sometimes there's one way and sometimes there's two. But in this case, there is two, and it's because we're looking for the amount of bacteria after 16 days. Our doubling time is 4 days. And so because I can take 16 and divide it nicely by 4, the doubling time, I can figure out the amount of bacteria in 16 days in the straightforward way. And here's how I'm going to do it. Is again, I'm going to look at the start. I had 800 bacteria. Now the doubling time is 4 days. So on day 4, I now have 1,600. On day 8, so I'm adding 4 days because the doubling time is 4 days, but I'm doubling my bacteria. I get 3,200. But I'm still not up to 16 days yet because another 4 days will go by and I'm on day 12. And again, I double my bacteria and I get 6,400. Again, adding 4 days to my time, but yet doubling the amount of bacteria. And so I add 4 days to 12, I get day 16. That's what I'm looking for here. I double my 6,400, which is 12,800. And there's my answer. So after day 16, or after 16 days, if you will, we have 12,800 bacteria. Now, I get find the amount of bacteria after 100 days. Now, you can see doing this table here, if I went now all the way to 100 days, it would take me forever. All right, and not all of the time can I do it, but 100 is divisible by 4. But I don't want to go all the way to 100. So here's what I'm going to do. I'm going to use my other formula that we had. The n is equal to n naught times 2, because we're talking about doubling times, T over D. Now, my n, I don't know how many bacteria I'm going to have after 100 days. But I do know my n naught. And that is, we start off with 800 of them. Time that's gone by is 100 days. And they have a doubling time of 4 days. Now I'm going to substitute into my formula to find out how many bacteria there'd be after 100 days without doing this whole huge chart. All right, so I have n is equal to, we got our 800 there, times 2. In brackets, I got T. Oh, our T and our D, because we're dividing them, have to be in the same units, which they are. They're both in days. So I have 100 divided by 4, I should say. The answer is 25. I'm getting a little ahead of myself there. Wrote that out. There we go. And we got a 4 there. All right, now I got to follow Bedmas. So the first thing is I actually got to do that, figure out that exponent to apply it. So I have 800 times 2, and 100 divided by 4 is 25. All right, now to follow Bedmas and do my exponent there. So I have 800 times, 2 to the power of 25. I get 33554432. All right, and if I multiply that number by 800, I get 2, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Whoo! We got a bacteria problem, big time. So that would be 26,800,000,000 bacteria would be around after 100 days. There we go. All right, so let's try another one of those. All right. A penny stock, initially worth 32 cents in the beginning, is worth $10.24 after 12.5 months. And the rise continues. Find the doubling time. So again, the doubling time, we have our time elapsed divided by the number of times it doubled. So write that in there. All right. Now, one of them again is already given to us, and that is the time elapsed, 12.5 months. Now what we're looking for is how many times did it double? Because it started off at 32 cents, and then we go to $10.24. All right, so let's see here. So I started off with 32 cents, and I doubled that number to get 64 cents. I double that number to get $1.28. I double that number, better get my calculator out here, to get $2.56. I doubled that number, still going here, $5.12. And then I double that number to finally get $10.24. Where am I going to put this? Right there, I guess, so I can fit it in. Okay, so how many times did it double? Count them up. We got 1, 2, 3, 4, 5. It doubled 5 times. All right, so now I take my 12.5 months and divide it by 5. And this time the doubling time is 2.5 months. Okay. Now it says how much is the stock worth after 10 months? So I'm going to see if this 10 is divisible by 2.5, because if it is, I can just do it the old school way here, the straight chart way. And so if I take 10 and divide, I do get a nice number. I take 10 and I divide it by 2.5, I get 4. So I can just do it the straightforward way. So again, let's see here. At the start, worth 32 cents. Now, 2.5 months later, it's going to be, whoops, get rid of that S. It's going to be worth 64 cents. Then I add 2.5 months, so I get 5 months. It's worth $1.28. Then I add 2.5 months again, so I'm at 7.5 months. I get 2.56, $2.56. And adding another 2.5 months, it is finally going to be worth $5.12. There we go. That's how much the stock was worth after 12 months, or sorry, 10 months. Now it says, how much is the stock worth after 24 months? All right, now if let's see, I take 24, divide it by 2.5. I don't get a nice number. So this is where, again, I am forced now to use my formula. Sometimes you're forced, sometimes you're not. So we have n is equal to n naught times 2 with the exponent of t divided by d. All right, so here we go. We want to know how much that stock is worth at the end, the final amount. We know at the beginning it is worth 32 cents. The time that has gone by is 24 months is what we're looking at. And doubling times, we figured out it is 2.5 months. All right, so now I'm going to substitute in my values. Well, I have n is equal to, n naught is our 32 cents. All right, our multiplying factor is 2 because we're doubling. T, we got a 24. So we have a fraction here for an exponent divided by 2.5. All right. So again, before I can do BEDMAS, I actually have to figure out what this exponent actually is. All right, so let's see here. Let's extend our page. So we have n is equal to 0.32 times 2. And then our exponent is 9.6. All right, now keep going here. And now I can do the exponent finally. So I have n is equal to my 0.32 times 2 to the power of, whoa, I already got it to the power of. So I got to take 2 to the power of 9.6 and end up with 776.05. All right. And then finally, timesing that by 0.32, here, 776.05 times 0.32. And I end up with, whoa, this stock's taken off. It's now worth $248.34. That actually happens sometimes if you're lucky enough. Not that I've been there, but it can. All right, so the key thing is that sometimes you can just do it the straightforward way. Sometimes because it's not divisible, you have to use our formula. And in the first example, I could have, for the 100 days, could have used the straightforward way, I guess, if you will, but it would have taken me forever and probably a sheet of paper. So it was actually beneficial for me to use the formula. But in fact, you can always use the formula. It's sometimes you just can't use the straightforward way. Oops. All right, and so